For 80 years, flying was a physical struggle against steel and wind, but by the early 80s, the weight of tradition had become an economic death trap for airlines. Every pound of mechanical cable was a pound of lost profit. Airbus saw an industry wall that Boeing ignored. They decided to strip away the hardware and trust the code. The A320 was a desperate rescue mission for an industry that could no longer scale. You see, to understand the Airbus A320, you have to stop looking at the airplane and start looking at the balance sheet of a struggling airline in the late 1970s. The story of this aircraft is often told as a tale of technological wonder, of digital computers replacing steel cables, but that framing misses the point. The A320 did not exist because Airbus wanted to be innovative. It existed because the global aviation industry had hit a structural wall and the existing fleet of aircraft was no longer capable of scaling to meet the demands of a deregulated, fuel-hungry world. By 1978, the airline industry was undergoing a seismic shift. In the United States, the Airline Deregulation Act had just dismantled the cozy, government-protected monopolies of the past. Suddenly, airlines were no longer competing on the quality of their steak dinners or the width of their seats. They were competing on price. This shift created an immediate, desperate need for efficiency. The workhorses of the era, the Boeing 727 and the early 737-200, were products of an era where fuel was cheap and labor was the primary constraint. They were mechanical masterpieces, but they were also incredibly expensive to operate. The 727, with its 3 engines and a requirement for a 3-person flight crew, including a flight engineer, was becoming an economic liability. Airbus at this time was a minor player. Their first aircraft, the A320, had proven that a twin-engine widebody could be reliable, but it was a niche product. They were the underdog, a European consortium often dismissed by the American giants as a political vanity project. But Airbus saw something that Boeing and McDonnell Douglas, blinded by their own success, had missed. They saw that the narrow-body market, the short to medium haul routes that form the backbone of global travel, was about to reach a breaking point. The problem was fundamental. Airlines were trapped by a weight of tradition. Every aircraft in the sky was a complex web of heavy steel cables, pulleys and hydraulic lines. To make a plane larger or more capable, you had to add more mechanical complexity, which added weight, which required more fuel, which decreased margins. It was a cycle of diminishing returns. Furthermore, the short-haul model was shifting from a few daily flights between major hubs to a high-frequency, point-to-point system. Airlines needed a plane that could fly 6 to 8 legs a day, turn around at the gate in 30 minutes, and do so with a level of fuel efficiency that was physically impossible using 1960s mechanical architecture. When Airbus began looking at a single-aisle successor to the A300, they realized that an incremental design, a slightly better 737, would be a death sentence. Boeing already owned that market. If Airbus built a conventional jet, they would be fighting for scraps on Boeing's home turf. They were boxed in. To survive, they had to rebuild the concept of a narrow-body aircraft from the ground up. They had to solve the constraint that was breaking the airlines, the escalating cost of operations, and the limits of mechanical scaling. This is where the true origin of fly-by-wire lies. It wasn't a choice made for the sake of innovation, it was an economic necessity. By removing the miles of heavy steel cables and replacing them with copper wires and digital signals, Airbus could shave several £100 of weight off the airframe. In the razor-thin margins of short-haul aviation, that weight is the difference between a profitable route and a bankruptcy filing. It allowed for more passengers or more fuel, which in turn allowed a narrow-body jet to fly distances that were previously the exclusive domain of much larger, more expensive widebodies. But the ambition went deeper than just weight. Airbus recognized that the single biggest cost for an airline, after fuel, was training and labor. In the traditional Boeing or McDonnell Douglas model, every aircraft was a unique island of technology. A pilot trained to fly a 737 could not simply step into a 747. The cockpits were different, the handling characteristics were different, and the type rating required months of expensive retraining. This created a training tax that grew every time an airline expanded its fleet. Airbus decided to use their new digital architecture to eliminate this constraint. Because the A320 A320's flight characteristics were controlled by software rather than physical linkages, the engineers could tune the handling of the aircraft. They realized that they could make a small aircraft and a large aircraft feel exactly the same to the pilot. This was the birth of Commonality. It was a strategic business moat. If an airline bought the A320, they weren't just buying one plane, they were buying a family. A pilot could move from an A318 to an A321 with minimal difference training. For a major carrier like Lufthansa or United, the savings in simulator time and crew scheduling were worth hundreds of millions of dollars. It was a systemic solution to a systemic problem. The development of the A320 was a period of intense pressure. While the engineers in Toulouse were rewriting the laws of flight, the American competitors were watching with a mix of amusement and genuine concern. Boeing's contender was the 737-300, a classic incremental fix. They took their existing airframe, put newer engines on it, and called it a day. It was the safe choice, the nobody ever got fired for buying IBM move. But the 737's 1960s architecture was already showing its age. Because the plane sat so low to the ground, Boeing had to flatten the bottom of the engine nacelles to keep them from hitting the runway. It was a compromise born of a refusal to start with a clean sheet. Airbus, by contrast, had no legacy to protect. They designed the A320 with a higher ground clearance specifically to allow for the much larger, more efficient, high-bypass turbofan engines that were coming to market. They weren't just building for the 1980s, they were building an architecture that could accommodate the next 40 years of engine development. The introduction of the glass cockpit and the side-stick controller were further responses to the operational wall. The traditional steam gauge cockpit were information overloads. Pilots had to scan dozens of mechanical dials to understand the state of the aircraft. By moving to digital color displays, Airbus could practice management by exception. The computers would only show the pilot what they needed to see when they needed to see it. This reduced pilot fatigue and increased safety, which in turn lowered insurance premiums and reduced the likelihood of costly accidents. The side stick itself, often criticized by traditionalists as a video game controller, was a masterstroke of ergonomic logic. By removing the massive control column from between the pilot's legs, Airbus freed up space for a fold-out table. It sounds like a minor detail, but for a pilot spending 8 hours a day in a cramped cockpit, the ability to properly review flight plans or eat a meal without balancing a tray on their lap was a significant improvement in the working environment. It signaled that the pilot was no longer a driver of a machine, but a manager of a system. The most controversial element, however, was flight envelope protection. This was Airbus's answer to the most tragic constraint of all: human fallibility. In the mechanical era, a pilot under stress could inadvertently fly the plane into a stall or a steep dive. The plane was a mindless slave that would follow a pilot's commands even if those commands led to a crash. Airbus decided that the software should act as a safety net. If a pilot tried to perform a maneuver that would jeopardize the structural integrity of the jet, the computer would simply refuse. It was a hard-coded limit designed to protect the airline's most valuable assets, the passengers and the airframe. This philosophy of protection versus the Boeing philosophy of pilot authority became the defining debate of modern aviation. But for the airlines, the logic was undeniable. A plane that was programmed to refuse to crash was a far more attractive investment than one that relied solely on the split-second reflexes of a human being in a crisis. The market's skepticism was put to a brutal test on June 26, 1988 at the Hubsheim Air Show. An Air France A320 performing a low-altitude flyover for a crowd of spectators failed to clear a forest at the end of the runway and crashed. The images of the brand new high-tech jet pancaking into the trees were a nightmare for Airbus. The critics immediately pounced, claiming that the computers had locked out the pilot. The narrative for months was that the plane was a dangerous, over-automated experiment that had failed its first real test. However, the subsequent investigation revealed a much more complex truth. The computers had actually performed exactly as they were supposed to. They had kept the wings level and maintained maximum possible lift even as the pilot flew the aircraft into an impossible situation, too low, too slow, and with the engines at idle. In a mechanical aircraft, the plane likely would have stalled and spun into the ground much earlier, resulting in a far more lethal impact. The crash wasn't a failure of the technology, it was a failure of human overconfidence, pushing the plane into a dead end that no system could escape. Airbus didn't back down. They knew that the economic logic of the A320 was sound. They spent the following years proving the reliability of the system through thousands of flight hours. The breakthrough came when Northwest Airlines, a major US carrier, placed a massive order for the A320. It was the first time a major American airline had turned its back on Boeing in favor of the European newcomer. The shot heard round the world had been fired. Boeing suddenly realized that their safe incremental strategy had left them vulnerable. As the 1990s progressed, the A320 family grew to include the stretched A321 and the shortened A319 and A318. The Commonality promise was being fulfilled. Airlines could mix and match these aircraft to fit specific route demands without ever needing to hire different pilots or stock different spare parts. The A320 was becoming the standard unit of global transport, but the real genius of the A320's clean sheet architecture wouldn't be fully realized until decades later. By the 2010s, the aviation industry was facing a new, even more daunting constraint: the carbon ceiling. Fuel prices were volatile and environmental regulations were becoming a major operational hurdle. Airbus once again found themselves at a crossroads. They could spend $20 billion to design a brand new aircraft, or they could leverage the flexibility of the A320's design. They chose the latter, launching the A320 Neo new engine option. Because the A320 had been designed with high ground clearance and a robust digital backbone, it was able to accommodate the next generation of massive, ultra-efficient engines like the CFM LEAP and the Pratt & Whitney geared turbofan. These engines were far larger than anything the original designers had envisioned in 1984, but the A320's forward-looking architecture allowed for the integration with relatively minor modifications to the wing and pylons. The result was a 15 to 20% reduction in fuel burn, effectively resetting the economic clock for the narrow-body market. The A320 Neo became the fastest-selling aircraft in history. This move effectively paralyzed Boeing. Their 737 with its 1960s low-slung frame simply could not fit these new, larger engines. To compete with the A320 Neo, Boeing was forced to perform an engineering act of desperation. They moved the engines forward and higher on the wing of the 737, which changed the aircraft's aerodynamic profile. To compensate for this change and prevent the nose from pitching up, they introduced a software fix called MCAS. The subsequent 737 MAX crisis was the ultimate vindication of Airbus's clean sheet philosophy. Boeing had tried to solve a 21st century problem with a 1960s airframe and an incremental software patch. Airbus, having made the difficult choice to break with tradition in 1984, had an architecture that could handle the evolution safely and naturally. The A320 Neo didn't just win on fuel efficiency, it won because its design wasn't a compromise. The A320's success also fit perfectly into the low-cost carrier (LCC) model. Airlines like EasyJet, Ryanair and AirAsia were built entirely on the back of the 320's operational logic. They didn't want a fleet of different planes, they wanted one standard unit that could be flown by any pilot, serviced at any airport, and turned around in minutes. The A320 provided the reliability and predictability that made the $30 flight possible. The A320 didn't create the model, but it certainly enabled its rapid expansion. It democratized the sky. Before the A320, international travel was a luxury for the few. Today, it is a utility for the many. This democratization changed the geography of the world. The A320's range, combined with its efficiency, allowed for the point-to-point revolution. Instead of everyone flying into a mega hub like London Heathrow or Atlanta to catch a connecting flight, airlines could now profitably fly directly from secondary cities, Bristol to Barcelona or Austin to Cancun. This bypassed the congestion of the major hubs and made the global economy more fluid and interconnected. By the early 2020s, the final evolution of the A320 family emerged, the A321XLR. This aircraft represents the ultimate breaking of the industry's constraints. For decades, transcontinental and transatlantic flights were the exclusive domain of massive four-engine wide-bodies. These flights were expensive and required high passenger volumes to be profitable. The A321 XLR changed that math. It allowed a single-aisle jet to cross the Atlantic with the same fuel efficiency as a short hop. Suddenly, an airline could fly from a mid-sized city in Europe to a mid-sized city in the US with only 200 passengers and still make a profit. It was the final nail in the coffin for the jumbo jet era. However, as the A320 becomes the dominant force in the sky, it also highlights the new risks of our digital age. In 2025, the industry is no longer worried about snapped cables or hydraulic leaks, it is worried about the integrity of the code. The A320's total reliance on software means that it is vulnerable to systemic risks that a mechanical aircraft would never face. A solar radiation event or a sophisticated cyber attack could, in theory, affect an entire fleet simultaneously. The very commonality that made the plane so successful is also its single point of failure. We are now entering an era where the pilot is becoming increasingly distanced from the physical act of flying. As we move toward single pilot operations and eventually autonomous flight, the A320 stands as the bridge between the mechanical past and the digital future. It proved that we could trust computers with our lives, but it also proved that we are now entirely dependent on the digital architects in Toulouse and Seattle. The next great wall for the industry is the hydrogen transition. As the world moves toward net zero, the current model of burning kerosene is no longer sustainable. Airbus is already using the A380 platform as a testbed for its Zero-E project. But hydrogen presents a challenge even greater than fly-by-wire. It requires a total redesign of the fuel system, the fuselage, and the global airport infrastructure. When we look back at the A320, we shouldn't see it as a collection of innovative parts. We should see it as a desperate and brilliant response to a world that was running out of room to grow. Airbus was forced into a clean break because the alternative was obsolescence. They took the technology of the gods, the fly-by-wire systems of the Concorde and the F-8 Crusader, and they gave it to the masses. They replaced cables with code, not because code was cool, but because code was light, flexible, and scalable. They replaced the control column with a side stick, not to be different, but to acknowledge that the pilot's role had changed from an athlete to a manager. They created Commonality, not as a feature, but as a weapon against the training costs that were strangling their customers. The A320 didn't just change the way airplanes are built, it changed the way the world moves. It is the architect of the modern sky, a machine that proved that when an industry hits a wall, the only way forward is a clean sheet of paper and a bold leap into the unknown. The reward for that gamble in 1984 was the dominance of the 21st century. But in the world of aerospace, the horizon is always shifting and the next revolution is already being drafted on a clean sheet of paper in Toulouse. Airbus didn't build the A320 because they could, they built it because they had to. And in doing so, they ensured that the future of flight would be written in the language of digital precision rather than mechanical tradition. The king of the current era is the electric bus, but as the first hydrogen test beds take to the air, we are beginning to see the first hints of what will eventually replace it. The cycle of pressure and response continues, and the A320 remains the most successful example of what happens when a company chooses to break the mold rather than simply try to fit inside it. The legacy of the A320 is found in the thousands of silent digital decisions made by its computers every second, keeping millions of passengers safe and moving the global economy forward. It is a testament to the fact that engineering is, at its heart, about solving the constraints that hold us back. In 1984, the constraint was weight and cost. In 2025, the constraint is carbon and complexity. The A320 solved the first. The next generation will have to solve the second, but they will do so using the digital foundations that were laid on a misty morning in Toulouse when a small side stick changed the world forever.